All right, we'll get started. Okay, so as you probably know, your assignments are due. Is there any questions about them? It's maybe a little last minute, but yeah.
Just a question about the last question.
Yeah. Yeah, that's right. That's right. Yeah. Yeah.
Explain each criteria.
Correct. Yeah. So the last question, you just do the one row, and you don't have to put it in a table format because it's just a row. You can just say point form criteria, what you gave for each of them. Yeah. Other questions?
Professor, why is the first one 84 and not 100?
It just added up to 84. So the marks are kind of, you can see that the marks kind of match what I ask you to do. So if I'm like, write 3 sentences, it's kind of like 3 marks or whatever. And so it just, at the end, I asked you 84 things. So yeah, that's why. Yeah. Last year it was confusing because I think, actually, yeah, the TA just sent back a grade. So people would get like 84 and they'd be like, why did I only get 84? And it'd be like, no, that's a perfect mark or whatever. But anyways, now that we use Moodle to collect assignments, it should be the case that Moodle is configured to show you your percentage out of 84. But sometimes that gets messed up too. Like the second assignment was like, Moodle was showing it was out of 84, but it's out of a different amount. So sometimes these things happen anyways. Okay, other questions about the content or anything? Okay, so I'm hoping that we won't have a full lecture, but we'll see how this goes. So what we're going to do today is we're going to wrap up the attack tree. So there's a couple topics still left to talk about. We still are in, I'll show you from here. So the entire attack tree, by the way, is on Moodle. So we'll talk a bit about the entire tree later, but you'll recall that we had 3 basic strategies. What can you see from outside the tunnel? How do you break into the tunnel? And how do you get the tunnel pointed at yourself? So one way to get the tunnel pointed at yourself is to get this certificate. And if you can get a certificate, then you can have the tunnel point at you. And we went through different ways of obtaining a valid certificate. Now, there's other things you can do besides getting a certificate. So first off, you might want to try to sidestep the certificate validation process. So that means you could do it without a certificate. You might try and use a certificate that's expired or revoked, or not use any certificate at all. And so these are the kinds of things that we'll be exploring today. Okay, so this is something we touched on, but I want to just bring it up again and describe historically what's happened in terms of this. So this is probably easiest to see with an actual example. So here we are on Moodle. And so Concordia has a certificate for moodle.concordia.ca. The certificate is signed by Global Sign. And Global Sign is signed by a root certificate that's in my computer and in your computers as well. Okay, so when Global Sign signs this certificate, actually, let me ask it a different way. This certificate in the middle, if we look at the certificate itself, you can see there's a whole bunch of stuff in the certificate, okay? Then we go down to the certificate that Concordia has. There's a whole bunch of stuff in it. And it's more or less the same stuff. So like this certificate and this certificate aren't really different in any sense. They both have like the same kind of stuff inside of them. Okay? And so the question is, if another thing is we keep seeing chains of exactly 3 certificates. Okay, so we see a root, we see an intermediate, we see a site certificate. it's not that unusual to see 4 certificates or 5 certificates, okay? That's not impossible. It's not against the rules or anything like that, okay? So if this certificate for Moodle.Concordia that Concordia owns is the same as this certificate, why can't Concordia issue a new certificate underneath it? So imagine a certificate chain of 4 certificates. So the global sign's the same, the second certificate's still global sign, the third certificate is Concordia, which Concordia owns. They have the private key inside that certificate that corresponds to the public key that's in that certificate. So they can sign whatever they want. So what if they created a certificate for Google and signed it, right? They signed it with the key that's in their certificate. That key is signed by global sign, and the global sign key is signed by the root certificate in my computer. Everything chains back, okay? So if you get a certificate, what stops you from issuing certificates? Issuing is just a fancy way of saying sign other certificates. So if you have a certificate yourself that is part of a valid chain, you could just go around and sign new certificates, okay? And so we need a way to distinguish a certificate that's allowed to sign new certificates from a certificate that is not allowed to sign new certificates, okay? And so inside the certificate, there's a field called basic constraints. It's right here. And it basically says that, that for this middle certificate from Global Sign, that they are allowed to issue new certificates. And that's designated by this flag certificate authority, which is set to true or to yes. Okay. There's also a path length constraint where you can say that you're allowed to sign certificates, and those certificates could sign certificates, but like the entire chain has to be within a certain length. So it's a way, it's sort of an indirect way of controlling controlling the like basically how far you can delegate your responsibilities. But I don't have anything to say about path length. That's just what it is. Now, if we go to the site certificate, so this is Concordia certificate, this is not allowed to create new certificates. So we should see that the basic constraints is set to false. So the basic constraints is here, and certificate authority is set to no. So this certificate is a certificate, it's part of a valid chain, but it's not allowed to extend the chain with new certificates or issue new certificates, okay? So when you receive a certificate chain, you check, obviously, that the chain is intact, but you also need to check that all the certificates that are not the site certificate have that flag set to be true. If they don't have that flag set to be true, then it is it's insecure. Specifically, if it's not set to true, then it could have been the certificate after it wasn't actually issued by a certificate authority. It's worth thinking about exactly what it means to not be secure. Okay, so everyone sort of knew this, and then what happened is Internet Explorer came out in, or I guess it was discovered in 2002. So a security researcher, basically what he did is he just, for fun, decided to take a site certificate and sign a new certificate as if it was a CA. And what he realized is that Internet Explorer never actually threw the error. So it wasn't checking whether everything in the chain was authorized to be a CA. And so anyway, so this leads to attack. So what does that mean? Well, that means if I can just get a certificate, which I can, anyone who owns a web domain can get a certificate for it, then I can pretend that I'm a CA and I can create certificates for any website that I want to. It will chain through my certificate and then back to the CA that signed my certificate, okay? But these browsers will accept it, okay? So I can man in the middle anyone and just create the certificate that I need. Okay, so everyone said, oh, that's really embarrassing. Microsoft screwed up, let's that's really bad on Microsoft. But it was kind of a stupid error. You know, I guess they didn't read the spec very closely. But anyways, no one will make that mistake again. It's too stupid. Then what happened is Apple came out with a new phone. They said, we have this new iPhone. And Apple's phone initially, I guess it's still true to some extent today, had a completely different operating system than their computers. Okay, so they had to rewrite an operating system. And so that meant rewriting the SSL stack. And guess what they did? They forgot to check this basic constraints as well. And so again, if you had any certificate at all, you could just pretend you're a CA and issue whatever certificate that you wanted. Then everyone said, oh, that's really embarrassing. It happened twice. It happened to Microsoft in 2000s. It happened to Apple in 2010. But now everyone really knows their lesson, right? This is never going to happen again. Then a bunch of IoT devices came out. And again, you're writing a whole operating system from scratch in most cases. Usually a very constrained operating system. And guess what? People, had to re-implement the SSL stack and they forgot it again. But don't worry, it's never going to happen again, okay? So these 3 times, it happened 3 times, but that's it. Everyone knows. So if you're designing a new operating system at some point, or you're working for a company that has a new operating system, this is one thing that you might want to check. Yeah.
You said that in last class that if the OS is upgraded, then the certificate changes. So can you explain?
Sure. So what I meant to say was actually kind of the opposite. So if a certificate that's a root certificate needs to change, you can only do it with a software update, like an operating system update. So it would have to be in the operating system to actually change it. Yeah. So root certificates are very people are very concerned about certificate authorities losing their root certificates because they're usually valid for 40 years, and not everyone updates their operating system all the time. Now we're better about that because there's all sorts of security issues if you don't. But yeah. But every time the operating system changes, most of the time there's not going to be any change to the root certificates. They'll be the same. That's not usual to change. Yeah. Okay, now here's another interesting case. So this was actually observed in the wild. So there were people in Syria, and they were trying to access Facebook, and they got a certificate that looked like this. So it was a certificate for Facebook.com, but it was issued by Facebook.com. Okay, so we call this a self-signed certificate, where it's a certificate that's issued by the same entity for the website is the same entity that's issuing the certificate itself. Okay, so there's nothing stopping you from doing a self-signed certificate if you want. So Concordia could do a self-signed certificate. I could do a self-signed certificate. There's nothing invalid about the self-signed certificate other than it doesn't have a chain back to a root certificate. Okay, so what does a browser do if it sees a certificate that doesn't chain back to a root certificate, right? Now, maybe 10, 20 years ago, people did self-signed certificates because they didn't want to pay a certificate authority for a certificate, but they still wanted encrypted connections. So browsers didn't complain that much. But now that the price of certificates have come down, they're basically free if you use something like the name escaped me. Let's Encrypt. You can do them for free. And so self-signed certificates basically aren't tolerated anymore. Okay? So if you observe this kind of certificate, your browser is going to complain about it. All right? So it seems like a stupid attack. Why would the adversary, if they're trying to man in the middle of your connection, why would they just drop a self-signed certificate? It's obviously going to throw an error in the browser. Okay? Well, let's think about what that error looks like. Okay? So this is what it might have looked like back in 2011. It says, there's a problem with this website security certificate. The security certificate presented by this website is not issued by a trusted certificate authority. Security certificate problems may indicate an attempt to fool you or intercept any data you want to send to the server. We recommend that you close this website and do not continue to this website. Click here to close this website or continue to this website. Not recommended. Okay, so put yourselves in the shoes of someone that's just trying to access Facebook. You don't know what a certificate authority is. You don't know what a certificate is. You don't know anything. Okay, you use a computer and you know a bit about connecting to the internet and things like that. You see a message like this, and all you have to do is click continue to this website, and you'll go to Facebook. Okay, what do you think people will do? Okay, they're going to click and go to Facebook, right? Not everyone, okay, maybe not 100%, but it's certainly not going to be the case that like 100% are not going to click on it if they see this, okay? So what adversaries could do is they could say, hey, we know that it's going to trigger a warning, right? And the browsers are like, don't worry about self-sign. Someone can drop in a certificate. It doesn't matter, we're going to warn the user, right? And the adversary might say, oh yeah, I would never try that because it's going to warn the user. But a smart adversary would say, hey, I'm going to do it anyways. And yes, it is going to warn the user, but I don't care because users just want to go to the website anyways, and they're just going to click through it. And the browsers make it so easy to click through, right, that you can do it. Okay, so there were some user studies that were done to they basically said, if you see this type of warning, would you actually try to continue through to the website? And the acceptance rate was, for this exact type of attack, which is called a domain mismatch, was basically about 50% of people would either yes or maybe click through when they were asked in a survey whether they would do it or not, okay? So if your goal is to man in the middle people going to Facebook, for example, if it's a targeted attack, you really care about one person clicking yes or no, you have a 50-50 chance, okay? If you're just doing some sort of surveillance, say you're a government and you're doing surveillance, you don't need 100% of people, right? If you can get 50% of the people and intercept their traffic, that's better than none at all, okay? So 50% is too high of a rate. Now, what people have done since then is they said, okay, this is actually a big problem. And so the browsers, starting with Chrome in particular, they sort of led the charge on it. They said, we got to do something about this. On one hand, if someone has a self-signed certificate and the user really wants to go to the website anyways, they should be allowed to go to the website, okay? We shouldn't prevent them, okay? But there's two kind of problems, I guess, with this type of error message, okay? One is it's way too easy to just ignore it, okay? So we gotta at least make it harder to click through, okay? The second problem with it is it's full of jargon. This actually isn't that bad. I've seen worse. But it's talking about certificates and certificate authorities and things like that, right? People don't know what that means. They don't know whether this is a serious error or a not serious error. And so the drive was basically to make it a lot harder to click through and to simplify the language a lot. So this is what Chrome might say, is it just says your connection is not private. Attackers might be trying to steal your information from this website, for example, passwords, messages, or credit cards. Okay, so it's a very clear, nothing about certificates or keys or certificate authorities or anything like that. It's just like, someone might be hacking you. Okay, and then there's a really big back to safety button. You can press that and you won't go to the website. And there is no, on this initial screen, there is no option to click through the website. There is an advanced field, okay? So you can click on advanced. Then if you click on advanced, it says, then it gives you like the technical explanation. The server could not prove that it's this website. Its security certificate is not trusted by your computer's operating system. This may be caused by a misconfiguration or an attacker intercepting your connection. and then you can proceed anyways, and it's marked unsafe, and then there's a technical error message type of thing. Okay, so this is a much better type of error. You have to at least click through in order to click through the website. You still can ultimately go to the website if you want to, and the language is a lot simpler. It's shorter. It's not like it's just one short sentence, and it talks about what the actual threat is to you as opposed to technical details about what went wrong. What went wrong doesn't matter. You don't care why it went wrong or what it is that went wrong. You care about like what's the threat to me. Okay, so this addresses it. And then if you want to try out what it looks like, you can. So let's see what Safari does today. These things are changing all the time. Okay, wrong hosts. So this is what Safari says today. It's actually very similar to Google's language. This connection is not private. This website might be impersonating this website to steal your personal or financial information. You should close this page. Close page. Okay. If you really wanted to, you could say, show me some more details. Safari warns you when a website has a certificate that's not valid. This may happen if the website is misconfigured or an attacker has compromised your connection. To learn more, you can view the certificate. If you understand the risks involved, you can visit this website. And then I click on it, and then there's another pop-up that says, are you sure you want to visit this website on a connection that is not private? And then blue is like what you're supposed to do or the default. And then if you really want to go, you can click through and then boom, you get there. Okay? So they at least try to steer you away from clicking through. It's not as easy to click through. They give you lots of warning, and they try and do it in plain language that's easy to understand. Okay, here's another fun attack that has to do with domain names. Okay, so let's say that you go to Concordia.ca, and I give you a certificate. It's perfectly valid. Actually, let me flip this around. I'm Concordia. I have a certificate for Concordia.ca. I want man in the middle you. I see you going to Facebook or Google or whatever. Let's go with Google. Okay? I see you going to Google. So what I do is you say, hey, Google, give me your certificate. And I'm in the middle. So I say, here's my certificate. But then I drop in my Concordia certificate instead. Okay? What your browser will do is it will pull in that certificate. It will read all the certificate information, and it will see, hey, this is a certificate for Concordia.ca. Then it will go, or it already has it because it's the browser. It will say, okay, what's the website that this person's trying to visit? Oh, that's google.com. Okay? And it will hold these two strings in memory. One's for google.com. One's for Concordia.ca, and in programming language, it will say, are these strings equal or not? Okay, and the answer is no, and then it will throw an error and it will reject the certificate. Okay, so that's what happens. So your browser inherently does this string comparison. Okay, now imagine that you're looking at a string and it's a little bit weird. Okay, it's not google.com, it's not Concordia.ca. The string you're looking at is google.com null character .concordia.ca. Okay? How would you, if you're a computer, what would you do with a string like that? Let me ask you this way. What domain is that string for? Why Concordia? Okay, someone say one thing really loud and really clear.
Main domain is Concordia.
Okay, and why do you think I'm not disagreeing with you, I'm just saying why. Like, think like a computer. Tell me what you did to reach that conclusion.
It ends at
Okay, so you started at the end of the string and went through. And what if I ask you, what's the full domain? So the end domain is Concordia.ca, but is this a subdomain? Is it google.com.concordia.ca? Is it google.com.null.concordia.ca? Okay, what if I tell you that null character is not valid? No domain is allowed to have a null character. Okay, now what are you going to do? Okay, you might just reject the string wholesale. That's actually the best thing. That's what you should do. Okay? What are some other things that you might do instead?
Ignore the rest after the space.
Okay, so let's think about ignore. So there's two things that we could do. So the first thing is we could actually just ignore the character itself. We could say, I don't know what that null character is. I'm going to drop it. If I do that, I end up with google.com.concordia.ca. Or I can ignore everything after the null string, after the null character. Why would I ignore everything after? Why, as opposed to just dropping the character I don't recognize? Okay, there's a very common answer, which is I might be running C. Okay, if I'm running C and I am told to go fetch a string out of memory, okay, what actually am I being told? What I'm being told is this is where the string starts. It's not like Java or something like that where there's a lot of like wrappers around the strings and I know how long it is and where it starts and where it ends. I'm just like, there's a string at this memory location. Go read it until you're done reading it. How do I know I'm done reading it?
In C, slash n is not that is the end of the string. So
Okay. So we call it a null character string, or null terminated string, because the null character is the character that ends the string. Okay, so I read it until I hit null, then I stop reading it. Okay, so if I'm C and I'm looking at this string, what's that? What domain is that for? That's for google.com. Okay, if I'm some other programming language that's going to drop the null character, what domain is that for? Concordia.ca or google.com.concordia.ca, which is a subdomain of concordia.ca. Okay? Now, if everyone in the world looks at this string the same way, it makes no difference which way you interpret it. Okay? You can interpret that as google.com, you can interpret that as concordia.ca, doesn't matter. Okay? If everyone looks at it the same. The problem is when different people look at it and conclude different things. Okay, if different people look at that string and they both think it means something different and there's an inconsistency, that's where you get the potential for an attack. Okay, so just to summarize what we said, if we see a string like this, we could just completely reject it. We could drop the character that we don't recognize. That would give us google.com.concordia.ca, or we could terminate at the null character. Okay, now pretend in a world where the first thing, let's say I'm concordia.ca, okay? Before I start showing you a certificate, I have to get it signed by the certificate authority, right? So I go to the certificate authority and I say, I have this domain, google.com null.concordia.ca, and I want a certificate for it, okay? Now, imagine, for example, that the CA is not programmed in C, and so they look at that domain and say, oh, that's kind of weird. I don't recognize that character, and they just drop it. Okay? So they're like, okay, this person wants a certificate. Remember, this is computers, not humans. So the computer program's just like, okay, this person wants a certificate for google.com.concordia.ca. I'm going to send an email to admin@concordia.ca, and if they can answer it, I'm going to sign the certificate. Okay? And usually when they sign the certificate, they're signing a verbatim copy of what you gave them. Okay, they're not pulling what they think the domain out is and putting in the certificate. They're not like copy pasting it. They're just like, you asked me to sign the thing with this weird string. I'm sending an email to admin@concordia.ca. You answered it. Great. Now I'm going to sign exactly what you asked me to sign, which includes the null character. Okay, so let's imagine the CA does that. So you're able to answer that email because you are concordia.ca. The CA is able to sign it. So now you have a certificate, but it's not exactly for concordia.ca. It's for google.com null.concordia.ca. Okay? Now you can go show that certificate to whoever you want. So let's say you send it to a user, and the user grabs it in their browser, and their browser is looking at the certificate. Now, let's say the browser's implemented in C, so it does that check. What website is the visitor on? Well, they're on google.com. Okay, I just got a certificate. What website's the certificate for? Well, it's for google.com. Oh, null character. Okay, that string's over, so it's for google.com. Does that certificate match the domain? Yeah, it matches. It's the same thing. Okay, no error, and then it goes through. All right. So this actually happened. There were CAs. There was a combination of CAs and browsers where this type of attack would work. And the reason was because they parse the strings differently. Again, I'm not telling you that 1, 2, or 3 is the right way to parse this string. Doesn't matter. You can parse it any way you want. The problem is that when different people parse it differently, that's when you get trouble. Okay. Now, another topic we can talk about is revocation. So imagine that, you go to a website, you say, do you speak HTTPS? The website says, yes, here's my certificate, okay? And you drop down a certificate. Now, imagine the adversary has breached concordia.ca and they get the key that's inside of that certificate, okay? What can they do with it? Is it enough for them to break that connection between you and the website?
Can I repeat the question?
Sorry, say it louder.
Can you repeat the question?
Yeah, sure. So if an adversary has the secret key that's inside of one of these certificates, what can they actually do? Can they break the connection that will form between the client and the server?
Intermediate CA?
So they steal Concordia.ca's certificate key. So you don't necessarily know the answer if you don't know the protocol, and you don't know the protocol if you don't know crypto and have taken 6110 and things like that.
If they hold the private key of the Concordia.ca, then they can forge.
Okay. So that's the right answer. So if you get the key, you can break the tunnel. Okay? So if the adversary gets the key, they can break the tunnel, so this isn't secure. Now, let's imagine that Concordia.ca have server logs, and they're going through it one day, and they realize, oh, there was a breach, and someone got into this server, or we notice that there's malware that's installed, and it has like a remote connection open, and we're not 100% sure that someone stole our key, but like the evidence is there that they could have. Somebody was in this system and had access to that key. We can't trust it anymore. Okay? What do? So first thing you'll do is you'll create a new certificate. No problem. You'll have to go get it signed by a CA, but that we said is fully automated now. You can send an email, click on a link, and that's done. Okay? So 5 minutes later, you have a brand new certificate, and it has a key that hasn't been compromised. Okay? So if an adversary is in the middle of that connection, right, what can they do? Can they break that connection? The same adversary that stole your old key.
They can maybe use the old.
Okay, what if they just use the old certificate, right? So you'll say, hey, do you speak HTTPS? The website will say, yes, here's my brand new certificate, 5 minutes old. And the adversary will just drop in the certificate from yesterday, right, that they know the private key for. And the browser and the client will accept it, presumably, unless if there's something else wrong with the certificate. But if there's nothing else wrong with the certificate, if it hasn't expired yet, and most certificates are valid for a year, then it's going to, if it accepted it yesterday, it's going to accept it today. Okay? So it's not enough to just reissue a new certificate. You can reissue a new certificate, and it's fine. That is a secure certificate, but you got to do something about the old certificate. Okay? So you need to cancel the old certificate. Now there's 2 certificates floating around. The adversary has one and you have one, okay? But you need to only have one certificate floating around, the one that you control. Okay, so Concordia gets a new certificate, no problem. The adversary will just replace when it sends down the new certificate, the adversary will just drop in the old certificate. So we need some way to cancel or revoke the old certificate. Okay, so how do we do this? How do we cancel the old certificate?
Timestamp.
Okay, so we can base it on time. The problem with it is that you would have to wait for it to expire. And you could have certificates. So this is actually a proposal that people have played around with, is why don't we, since you can automatically get a certificate in an automated way, what if certificates are only last a day or 3 days? So we call that a short-lived certificate. So every 3 days, your computer goes and gets a new certificate. Okay. Then if you lose a certificate, the adversary can use it for a day or two, depending on when they seal it, and then they're out of luck. Okay. So that is actually a sensible solution to the problem, but it just never took off. CAs don't like it. They don't like the infrastructure. Websites are like kind of weird about like, well, what if something goes wrong and I can't get the certificate renewed, and now I'm going to lose money because I'm an e-commerce website and things like that. Okay, so websites like having a certificate that will last a year or 2 years. Okay, so that doesn't work. Okay, so the first option we can do is we can try to figure out whether a certificate has been revoked or not. So I receive a certificate. That means I'm going to go ask whether this is revoked or not. And the question is, well, who do I ask? Sorry? Okay. So who's a trusted third party in this ecosystem? Okay, a certificate authority would be one. Let's start with a simpler example. Could I just ask the website itself? Hi, Concordia, what's your certificate? This is my certificate. Hey, Concordia, is this certificate revoked? No. Do I trust that?
No.
Why not?
It's not on the HTTPS.
Okay, so, well, even if it's over HTTPS, it could still be the adversary because the adversary has the old certificate. Okay, so if the adversary can replace the certificate, they can make an HTTPS connection, and then they can say, no, not revoked, not revoked, not revoked. Okay, so I can't ask the website itself. So what I have to do is I have to go up the chain one. Okay, so where did the website get the certificate from? Well, they got it from a CA, so I'm going to go ask the CA. Okay, and if you look inside certificates, they'll tell you where to go. And it usually is the CA. Technically, I guess you could redirect them anywhere you want. But if you go look inside the certificate, it will have the URL where you can ping to ask whether this is revoked or not. So this is called the Online Certificate Status Protocol, OCSP. And so this is an example, for example, of what the URL looks like for a global sign. Okay, does anyone think of a problem with this?
Yeah, attacker can be between the verification.
Okay, and what happens? Look at the URL for a second, and then think about what the adversary can do.
It's going on HTTP. It's not on
It's an HTTP.
Okay, so what can the adversary do? Hi, global sign. Is this certificate revoked? Global sign says yes. The adversary's in the middle. It's over HTTP. What can the adversary do? They can just change the response. Okay, so that's one thing that can go wrong 100%. Okay, I'm going to save. I have a question for you, but I'll save it for a second. Okay, let's say you're a CA. Okay, what does that mean for you? Okay, think about this from a deployability standpoint. You thought about usability, deployability, security a lot, probably over the last week. So from a deployability standpoint, you're a CA, you signed a certificate for Concordia, okay? Are you done? Are you like, okay, I signed that certificate, I don't have to do anything anymore? Okay, this protocol tells you, no, you're not done. Okay, so what do I have to do in addition to signing a certificate?
Right.
So I have to validate it, and what does that mean, like concretely?
Receiving the request and updating providing the response.
Okay, so I have to put up a server, and that server needs to be online, and people are going to ask me about whether the certificate is valid or not, and I have to say yes or no. Okay, so I have additional costs because I have to maintain this server in real time. Okay, now let's say you guys are like, this CA thing is great. You just have to sign things, and people pay you thousands of dollars to sign things. I want to be a CA, right? And let's say you're a really good CA and everyone loves you. So Google comes to you and says, hey, we want you to be our CA. And you say, great, I'm going to be Google CA. Then Facebook comes and they say, I want you to be a CA. So now you've signed up Facebook. And then Twitter comes the next day and now you've signed up Twitter. Okay? What does that mean for this poor server here? What it means is every single time someone goes to Google, they also hit your server saying, is this Google certificate valid?
It's kind of DOS attack. They need to distribute their data centers.
Okay, so are you going to have a lot of bandwidth? Yeah, you're going to have to, every single connection to Google and Twitter and Facebook is also going to ultimately result in a connection to you. Okay, what's going to happen to your poor server probably? If all of Google's traffic came to you, you're a CA, do you have like Google's infrastructure? You know, they spend so much money having like data centers all over the world and things like that. Does any CA have that kind of infrastructure? No, they don't, okay? So what happens is these things go down, okay? Now, what does that mean for the browser? So now imagine this scenario. Hey, global sign, I have this Concordia certificate, is it valid or not? No response, okay? I wait 5 seconds, no response. I wait 30% seconds, no response. What do I do?
There is a one flag TTO and like it's wait for certain time period. If not getting response, it's depending on the browser. Maybe some browser allow, maybe some browser drop the request. If
Okay.
it's not open world and close world assumption.
All right, let's say the browser drops the request. Okay, what does that mean? I go to concordia.ca. The page is like loading for 5 seconds, and then it's just like, oh, sorry, like can't, certificate error, can't validate whether it's revoked or not. Sorry. Okay, do you think users would be happy with that? Okay, what if like every other website you went to, you got this kind of error, right? The web would be basically not usable, okay? So what are browsers going to do even though it's not the secure thing to do?
They just pop up the warning and then allow us to.
Okay, well, even a warning. Hey, Concordia, warning, 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 revoke certificate, you know? You go to Facebook, warning, warning, warning. Are you going to be happy with that? No, okay? So what browsers do actually is they do nothing. Okay, they do send the request, and if they don't get a response, then they just say, we can't be warning our users all the time, right? And so we just do nothing, okay? So what's even easier than an adversary that's in the middle that can intercept the traffic and change responses because it's over HTTP? Pretend this actually happened over HTTPS. Okay, now you can't change the stuff in the middle, but what could you still do? You could just drop the packet. Okay, you drop the packet, it fails open. So this is a security concept that we have. If you can't get the check done, you're going to fail. And so do you fail in a permissioned way or a permissionless way? Do you fail open? Do you fail closed? The power goes out at the parking garage. Does the arm go up or does it say shut? Right? Let's say the fire alarm goes off and the power goes out in this room. Are the doors going to stay locked, keeping everyone trapped in the room, or are all locks going to like open so that people can get out? Right? So lots of systems fail open. This is a system that fails open. Okay, so congrats, you're the CA for Google, Facebook, and Twitter. You're going to get swamped, and you're going to fail open. Okay. Now, you also notice it's over HTTP. That means that the adversary can change it. The one question I want to ask you, though, is why HTTP? Why isn't that HTTPS? Okay, it is a certificate validation, but why can't that? If it's over HTTPS, then pretend that we lived in a world where things would fail closed, and CAs would put up servers that were big enough to handle this traffic, and now they're forced to more so than they were before. So there's new guidelines and things like that, and for certain types of certificates, they have to prove that they can handle all this traffic. Okay, so let's pretend we live in that world. So the adversary can't drop the packet. That attack's not going to work. But in this case, the adversary can still change it, right? So why not HTTPS? With HTTPS, they can't change the packet anymore, right? They can't change the response from yes to no.
The question is that how you validate the certificate
How do you validate which certificate?
of the PTV?
Okay. All right. So here's what happens in slow motion. Pretend this was an HTTPS certificate. Okay. So I go to concordia.ca and I say, "Hi Concordia, I want to talk HTTPS." And Concordia says, "Great, here's my certificate." Then I say, "I don't know if the certificate's revoked or not. Where should I go?" Well, I should go to HTTPS globalsign.com. Okay. So then I go to GlobalSign, and what's the first thing I say to GlobalSign? I say, "Hey, I want to talk HTTPS." And GlobalSign says, "Hey, here's my certificate." And then I say, "I wonder if this certificate's revoked or not. I should go look." So then I go look in that certificate, and it tells me, "Oh, go over to this other GlobalSign server." And that's over HTTPS. And I say, "Hey, give me your certificate. I want to talk HTTPS." And they give me the certificate, and then I say, "Oh, I wonder if this certificate's revoked or not. I should look up where I need to go. Oh, here's an HTTPS address. I should get that certificate." Okay? And so you end up in this continual loop where you can't break out of it because you can never form the HTTPS, you can never complete the HTTPS connection without validating a certificate. And you can't validate the certificate until you know whether it's revoked or not, and that's what you're trying to do. Okay? So that's actually why it cannot be over HTTPS. It has to be over HTTP. So there's a circular dependency.
Professor, can you explain fail open?
Yeah, so fail open just means that if there's a failure mode, then you can think about whether security systems stay turned on or turned off when there's a failure. Yeah. So the examples would be things like a door that's normally locked. Let's say there's a power outage, so that's the failure. Does the door stay locked or does it open? Right. So both are fine, but you have to think about what the consequences of them are. Right. So if it's some sort of emergency situation, keeping the door locked. And people, maybe it's like an electronic door where you have a badge and you can't open it because the system's down because the power's off, then people are trapped, right? So that's an example where it might fail open. Similarly, with a parking garage, if the arm is down and the power goes out and no one can pay, or say there's a bank failure or something like that and people can't pay, they're not going to say, "Oh, you can't leave until we get the power back on," right? They're just going to open it up and let everyone leave. So those are examples of things that fail open. But you could also fail close. So in this case, if I ask for to know whether a certificate's revoked or not, the failure is I don't get a response. Yeah? So now I have to decide, do I go ahead anyways as if it's not revoked? Or do I assume the worst and assume it is revoked? So if I assume the best, that's like fail open. And if I assume the worst, then it's fail closed. Does that make sense? Okay. So these are also sometimes called deny override or permit override. So permit override would be the same as fail open. The override condition is that you permit it, and fail override would be the opposite. Deny override, sorry, is the same as fail closed. So you'll see this in security a lot. I mean, basically any system could fail for any number of reasons, and one of the things you need to decide is, are you going to fail open or fail closed? And even before this course is done, you'll see a couple other examples of them, of this, yeah. Okay, so without HTTPS, then the adversary that's in the middle, Alice says, "Hey, is the certificate valid?" The adversary changes the answer no to yes, or even more simply, they could just drop the response. Yeah.
Could you go back to so you said the status check. So do the browsers do the status check?
Yeah.
Global sign and all the CS.
That-
How often do they do?
Yeah. Okay. So how and when, who does it, how do they do it, and when do they do it? Okay. So the browser does it. The browser knows how to do it from the certificate itself. So it will do it at the time that you ask for a certificate. So I go to this domain. Let's say I haven't gone to this domain in a couple days or whatever. Then I'm getting this certificate for the first time. I've never seen it before. Then before I show the lock, so it's already too late. The lock is being shown, so this check has already been done. But before I decide whether to show the lock or not, I'll go into the certificate, I'll grab the URL of where I'm supposed to go, and then I'll hit that URL, and then I'll ask for the response. Yeah. And then the other question is sort of like, do they cache like responses? And the answer is probably yes. So I don't know all the inner details, but I can't imagine that they wouldn't cache it for a couple days or something like that. So if you go to a website like Wikipedia and you download 80 images in order to put that website together, you are getting the certificate 80 times. Are you doing the revocation check 80 times? Probably not, right? You probably, I imagine they remember it for either till the browser closes or 3 days or something like that. I don't think they would cache it more than 3 days, but I don't know what the number is, yeah. Okay, a second thing is you can have the CAs just make a list of all certificates that they've revoked. Okay? Now, this is almost the same as using a status check. Okay? The main difference with it is you're not asking on a one-to-one basis. Okay? What you're doing is you're getting a whole batch of them. So in a sense, for the user, it's less efficient because they're getting an entire list that contains a bunch of websites that they're never going to visit, and they don't care about whether those certificates are revoked or not. Okay? But the benefit of it is that the CRL can be signed by the certificate authority. So the certificate authority could sign it, and then that stops someone in the middle from basically messing around with it, even if it's served over HTTP. Okay, they'll just sign it with the same key. Now, you do have to ask the sort of recursive question of whether this certificate authority signature is still valid because it didn't lose its key. But then you would get the CRL for whatever CA issued it, and then eventually you would have all the CRLs, and then if the certificate isn't anywhere on the set, then you would believe it. Okay? So now, because status checks, they're basically across time, things sort of change. So for a long time, browsers tried to do the status check, and it would always fail, and that was just the world that we lived in. Then people pushed back and said, no, this is pretty serious. You got to do something better than that. And so what browsers did is they said, okay, we're actually going to turn off OCSP. We're not using it anyway. It doesn't work half of the time, so we're just going to turn it off. And what we'll do is we'll go ourselves as a browser vendor, like Google the company, we'll go to all the CAs, get all their CRLs, their certificate revocation lists, all the bad certificates. They might go once a day, and then they'll push that list to all Chrome users. So you'll receive it. It's not a software update. You don't have to click on anything, but your browser will just sort of update quietly in the background, and it will get the new set of all certificate lists. Okay?
Is it like a DNC list?
DNC stands for?
Do not call, but yeah.
Okay. Yes, sort of, I guess, yeah.
And they do it every time so the browser does it automatically, and they store it in the memory of mine.
Yeah, that's right. Yeah, so Chrome is hooked up to receive these requests from a server at Google. It sends it over like some custom protocol between Google servers and with Chrome. It's stored on your computer. Yeah, and then it updates, I think, once a day, something like that. So revocation lists, yeah, I think it's sort of like a daily kind of thing. So this could work well in principle. There was some criticism. This is like quite old. It's almost 10 years old, so I don't know what the latest data is, but one study from 2014 found that even though in principle it works, the number of CAs that aren't being checked is really high. So it's something like 75 or 85% of CAs are just missing from the list. And we don't know why. Like, is is Google not going to those CAs, or Apple or Microsoft, or is it that they aren't issuing their lists, or they're in a wrong format? Like, we don't know the reason why, but anyways. So this was thought to be like a nice idea in principle, but it only works if everyone participates, and not everyone was participating. And so in terms of actual security for end users, it wasn't great. Now, the third thing that you can do, which I think is coming back now. Oh yeah, I should say that in terms of history, so for a while we dealt with OCSP even though it didn't work. Then for a while we tried the CRL set. Then we kind of went back to bullying CAs into doing OCSP better. So we said for certain kinds of certificates, these EV certificates, you have to do there's some new rules for these certificates. So if you want to issue these certificates, you have to register them in a list of all certificates called certificate transparency. You have to have a responder for OCSP that is responsive, and we're going to test it on occasion. And if we find that it doesn't work, then we're going to revoke your certificates, or we're not going to trust your routes, or I don't know what the exact consequence was. Then there's a third option that actually works really, really well. The third option is that instead of every user that goes to Google and gets Google's certificate hitting the CA for some sort of revocation check, why doesn't Google just go to the CA, ask for the revocation check, and then what they can do is they can staple it in when they send the certificate down. So they'll basically send you the certificate, and then they'll also say, here's like a signed document that's only an hour old, and it's from the CA, and you can check that the key matches, that signed this matches the key that's in the CA certificate, and it says the certificate is still valid. Okay? If Google sends that to all their users, then instead of 1 million users a second hitting the CA, Google's hitting it once an hour, just once, and then Google is, they have the infrastructure anyways, and so they just send it down. So this is probably the best solution. The problem was that when you put this extra information into the headers, that there were some middle boxes in the internet that just broke. They didn't know what to do with this extra information. It was in a weird format, and so they dropped the packet and things like that. So basically people said this is the best, but until middle boxes don't drop packets that include this, it's not reliable, okay? And websites, they care about reliability amongst all other things, right? Reliability is like number one. So if there's a chance that your packets aren't being received or connections are being dropped, they don't want to risk it. And they don't control every middle box, and there's a lot of mailboxes on the internet, and they have customers all over the world that take all sorts of different paths through the network to get to their websites, okay? So they can't control all of that type of stuff. Now, infrastructure updates, there's now standards for how to do this, and so things that are compliant with the latest standards will not drop these types of packets, and so eventually we'll evolve to the place where this will be not a problem anymore. I don't know if we're there yet. I've read stuff recently about stapling, but I don't know what the current status of it is, if it's now like widely deployed by websites, or if it's still like sort of in this experimental phase. But anyways. Yeah.
By stapling, the server is, how does this work?
Yeah, I should have drawn a picture. It would have been better. So normally I go to Google, they give me a certificate, then I go to the CA and they give me a yes, no in terms of it being revoked. Okay. The problem is if there's 1,000 me's that are going to Google, there's also 1,000 of me's going to the CA. So what Google does instead is Google says, I'll go to the CA for you. So Google goes to the CA, gets the not revoked status. In this case, they have to get it signed or something like that, so that because I don't know whether they use HTTPS or not when they got it. So they get it signed. And then when I go to Google and say, hey, give me the certificate, they're like, yeah, here's the certificate, plus here's the CA recently attesting to the fact that this is not revoked. So you don't have to ask them, I ask them for you, right? So they give it to all 1,000 people who are asking for their certificate. And then the CA is comfortable because they only get asked by Google once an hour instead of getting hit 10,000 times a second.
So when you say we ask Google, do you mean the browser?
Yeah, so the browser, I forget at what step, but everything is browser. It's never a human. It's always the browser, right? So I type in https.google, my browser knows to ask for the certificate. When it gets the certificate, it knows it has to check the revocation, and it goes, finds the URL where it's supposed to check it, goes to that URL, tries to get a response. And all that happens automatically. It happens like faster than you can even see the page load, and then it's either done or not done. Yeah. Cool. Okay, other questions about this? Okay, another attack that we could do is just not use a certificate, period. Okay, if we can keep a user on HTTP instead of putting them on HTTPS, then we can always intercept their traffic. Okay, so let's say our goal is just to keep everyone on HTTP. I can't control what websites do. They're free to deploy HTTPS. They can get certificates and all that stuff. As an adversary, I can't control it. But what I could try to do is control whether users end up going to the HTTPS versions of websites or they go to HTTP versions. Okay? So my ability to do this is going to depend a lot on exactly how things are configured. But one attack that worked for a while, but now everyone knows about it, so they code it up differently. So Concordia is not vulnerable to this attack, so I'm going to pretend fictitiously that this is how it was done. But imagine that I go to Concordia, and there's a website like this, like where there's a little sign-in button at the top. And sometimes right from the root screen, there's a username and password field right there, okay, and you can submit it. So just sort of imagine that on a website. And imagine that the website itself was on HTTP. So I go to Concordia and it's like, here's an HTTP version. Up in the right-hand corner, there's a sign-in button, there's a username, there's a password. And should I send that password over HTTP? No, I shouldn't. But what if the website configured so the submit button, when you click it, it would go over HTTPS? Okay, so the website, you're looking at an HTTP page, but the submit button is wired to HTTPS. The password will go over HTTPS, so is that safe? Why? How do you know whether the button goes over HTTPS or not? Okay, so let's assume for a second that somehow you know. Okay, you don't, you're right. Let's assume that somehow you know. Is it at least safe if you somehow knew?
If we know that for sure it's going over HTTPS.
Yeah. Okay, so that's right. So if you know for sure it's going over HTTPS, it is secure. That was the first answer I'm looking for. The second answer I was looking for is, well, how do you know it's going over HTTPS? So how do you know? Okay, yeah, sure. You can sniff the traffic or something like that. Let's say you sniff it and it went over HTTPS. Or sorry, HTTP instead of HTTPS. Now what? Oops, right? My password's gone. I realize now that was a mistake. But can you get your password back? You can't, no? Okay. So what else could you do?
We can do like check intercept.
Okay, forget about trying to intercept the connection. I'm talking like a normal user, not you guys. Okay, normal user, they're say at their computer, they're wondering whether if I hit submit and my password's about to go over the wire, is this going over a secure connection or not?
Maybe it's like a symbol or something.
Okay, so what if there's a submit and then there's a little lock beside the submit button on the website itself? Like it says submit and there's a little button, the button's red, it's bright red, it has the word submit, there's a little lock there. What does that tell you? Okay, that would tell you nothing because it's just a picture on a website, right? Anyone can put any picture on any website. What if you hover your mouse over it? Sometimes it depends on how the website works and how your browser works. Sometimes it will show you a URL maybe in the bottom. You could check that to see whether it's HTTPS. Okay, but let's say you're hovering your mouse over it and it's not showing you anything. Okay, so the last thing that you could do is you would have to look at the HTML of the website. Okay, if you looked at the HTML, you could see whether that button is going to go over HTTPS or not. Okay, so that's more or less the only way that you would know. Now, is an average user going to inspect element and figure that out? No, obviously not. Okay, so for an average user, they don't know. Okay, all right. So now you're an adversary. You're in the middle. Let me grab some of these slides first. Yeah, okay, so this is what you're supposed to do. So you would click on it, you right click, inspect element, you would see some like sign in button, and then you would look and you would see, oh, there's HTTPS here, and so this is fine to click on or not. Okay, now let's say that there's a adversary that's in the middle, okay? And let's say that this website is configured correctly. Okay, so it is, that submit button is indeed wired up to send the password over HTTPS, but the adversary still really wants your password. Is there anything that the adversary can do?
Could you repeat the question?
Yeah, so the adversary really wants your password. They're in the middle of you going to Concordia. So this is what they see. They see you ask for Concordia.ca's index page, which is over HTTP. So you download that. And they know that inside of that website, there's a submit button where you can put your password. They also know that if you were to type your password in there and hit submit, that you would open up a new connection to Concordia over HTTPS. And only after you have that secure connection in place and that tunnel in place would you send the password. And the password would go over that tunnel. And the adversary won't be able to get it once it's over the tunnel. So is there anything the adversary could do to try and still nab your password?
You can change the HTML
Okay.
element.
All right. So what would the net result be if the adversary changed the HTML so that submit button was now wired to go over HTTP instead of HTTPS? Yeah, so it's sort of like a downgrade. Yeah. So in that case, your password would go over HTTP, right? Okay. Can the adversary actually do that?
Yes.
Why?
Because it's HTTP, he can intercept.
Okay, it's over HTTP, so the adversary can modify and view. Okay, how hard would that be? You would have to like find that exact button. You would have to know something about Concordia. Let's say it's an adversary and they just want all your passwords, and they've never heard of Concordia University, but they're greedy and they're just in the middle. They're trying to grab every password that you might type into any website ever. And if you type one into Concordia, they've never heard of it before, but they still want it. Okay, can they do this, or is this like a custom job where they would have to know that exact button? They would have to know exactly where it is in the HTML. They would replace it, make sure they don't break like the entire website. So is this like a sort of custom tailor-made attack, or is this like a generic attack that just works on any website?
It's a generic attack.
Okay, why generic?
You can script it.
Because you can downgrade all HTTPS connections.
Okay, so what you can do very simply is just say, go through this HTML file, and every single time you see the word or the characters HTTPS:// replace it with HTTP://. Okay, you just do it. You don't know what you're doing. You have no idea. But basically, every link that's on that website that would normally go over SSL is now going to go over HTTP instead. Okay. Now, the servers may not like that, and the servers might say, hey, I don't talk HTTP. So there might be some errors for it. But anyways, you can sit in the middle, you can do it, and then you can just log everything. And then, in a week, a month, a year, you can go through your logs and see what you got in terms of passwords. Okay. So there's schools that do this. SSL strip is the main one. And yeah, it's super simple. Okay. You downgrade every single reference in every HTML file or PHP file or whatever from HTTPS to HTTP.
But it's not possible in SSL 1.3, right?
It's not to what? Possible to?
TLS in 1.3.
No, this stuff has nothing to do with TLS at all. So you're just changing the HTML files themselves so that they never even ask for TLS. So it doesn't matter what version of TLS works. Yeah. So you're correct that downgrade, like what we talked about when I used the term downgrade before a couple lectures ago, that kind of thing isn't possible in 1.3. And that's more of a specific like downgrading the version or downgrading the cipher suite that's used and that type of thing. This downgrade maybe isn't the best. Stripping's a nicer word maybe to distinguish it from downgrade, but it is kind of the same idea. In this case, you're just replacing every link that the user ever sees with an HTTP link. Okay? So if you ever start on HTTP, then the adversary can do this attack and they can keep you from ever leaving HTTP. Okay? So you'll never leave HTTP because every time you try to, you would need to follow a link to go to HTTPS, and the adversary is going to replace it. At least you'll never leave it if you're just clicking on things. Okay, if you go up to the URL and type HTTPS, then you might leave it. Okay, and so the only solution, well, there's a couple solutions, but the main one is that you need to move the entire website to HTTPS. Okay, so the mentality for a long time was, we'll use HTTP for the stuff that doesn't matter, like Concordia's homepage where there's just news articles and things like that. That stuff's not sensitive. It doesn't matter. That can go over HTTP. When the user logs in and we take their password and we're showing them their student accounts and their transcripts and things like that, that stuff needs to go over HTTPS. So we're going to have this hybrid website where the non-sensitive stuff will go over HTTP, and then when they log in, we're going to switch them over to HTTPS. Okay? SSL stripping says you can't do that. You need to do HTTPS even for the non-sensitive stuff. Okay? And now you'll notice the web is that way. So even if you go to Concordia, right, and you just go to their basic website, like their landing page, you'll see that it's over HTTPS. Okay? There's no reason necessarily that this had to be. Now in this case, I'm logged in and there's cookies and things like that, but there's no reason that this would necessarily have to go over HTTPS other than this SSL stripping attack. Okay, here's another thing. By the way, I'm going to go through the break because we're going to end early, so you'll get the time of the break back. Yeah, back. Okay, so pretend you go to this website, and this is what you see. Okay, there's a pop-up, and the pop-up's for PayPal.com. You can see that the pop-up window is over HTTP. You probably can't see it because it's pretty small, but if you were to look really closely, you would see that this is SSL. There's the lock. It's even an EV certificate. It's green. There's a username, password. I could put my username, password here, and I could click login. If I click login, am I happy or am I sad? Okay, is that secure? Is my password secure if I click login on this particular website?
No.
Why not?
It's a pop-up.
Okay, so it is a pop-up, but it's still over HTTPS.
But it's going to the HTTP on the outside of the picture.
Okay, so explain that a little bit better.
When you type the password, it's going to the main frame where you type the password, and then it's go to picture in picture. So it executes after it's passed to the second phase.
Okay, so if I put the password in here and I click send, isn't it just going to go to PayPal.com?
First, it went to conflict.
You don't have to look ahead. Just guess.
Can you repeat?
Yeah. So I just want to put my password here and click login. It's that simple. I'm on PayPal.com and it's over SSL. There's no problem, right?
No, but it will go to first your browser, main browser, then it go into picture in picture.
What's picture in picture?
It's second window in the browser, like second kind of calling a web application from web browser again.
Okay. Okay, pretend this word picture in picture isn't here. So you're kind of right, but you're not exactly getting it exactly right.
Professor, so I'm
Yeah.
not getting it, which is an HTTP.
Okay, so there's just this pop-up, it's sitting there, it says paypal.com, there's a lock, and there's a username, password, why can't I log in?
So after you type in your username and password, from this pop-up window,
Yeah.
your credentials will go through the HTTP connection, and then it will go to PayPal or whatever HTTP standard.
Okay, there seems to be some confusion about pop-ups. So a pop-up window is just, it's just a window. Like it's just like you could have two tabs open, you could have a pop-up in another window, so the fact that it's a pop-up doesn't change anything about where the message is routed. So typing in a pop-up is the same as typing in a not pop-up. Yeah.
Pop-up can be designed by the coding. Like if you know the code, you can create a pop-up design. You can show the lock as well if you want.
Okay. Is this actually a pop-up window?
No.
How do you know?
No, pop-up is like a square, like a rectangular thing.
Okay. So the web changed actually as a result of this, but it used to be the case that a website could ask for a new window to be opened, and it would just be a new browser window, and it would just sort of hover wherever it popped up. So there's nothing about the look of this that makes it not a pop-up window. Okay, is there any reason that this could not be a pop-up window? Or is there anything like kind of sketchy about this at all?
The only thing I can think of is you have the browser,
Yep.
and within the browser you have like something like another browser.
Yeah, that's right. Yeah, so it's a new window. It's just a new copy of the browser, but the one window is like smaller than the other window.
Oh,
Yeah. So, have people seen pop-ups like this, or is it completely? It's you don't see this today at all for this reason. I'm going to tell you the reason why. You see new tabs, so things will open up in new tabs. Sometimes it will create new entire windows. Sometimes it will give you a dialog box or something like that. So there are things that a website can ask to be spawned, but generally you wouldn't see another entire copy of the browser that's in a separate window that's smaller than the bigger window. Okay? Now the only concern I have with this is just that if you look at how this window's positioned, it's entirely inside the outer website. Okay? So the outer website is from here to here to here to here. And this pop-up browser is completely inside of it. Okay? So how do you know that that's actually a window as opposed to, say, an image that's on that website? Okay, so let's say I try to move it and it actually moves. Does that prove it's a pop-up?
You can move it out of the pop-up.
Okay, so that's the thing. So if I start dragging this thing around, you can with JavaScript have objects on websites move around. Okay, that's not a problem. But yes, if I try to drag this outside of the window, outside of the space that the website has, and it doesn't go, then I'm thinking, oh, maybe this is actually sophisticatedly programmed inside the website. Okay? Every time, okay, you probably don't see pop-ups anymore, but pretend that 10 years ago, you're on the web, you're an everyday user, and you see something like this, and it's pretty normal, like there's lots of pop-ups, it's not unusual. You always check by dragging the window around the browser, right? That's something everyone does. Everyone knows that every time you get a pop-up, you need to drag it all around your screen to make sure it's a pop-up, right? No one knows that, right? Okay. Now, let's say that this is just an image, maybe a movable image or something like that, that's inside of this website. and I put my password in here and click login, is that going over HTTPS to paypal.com? No, it's going over HTTP to this website, or whatever the button's configured to do. Okay, so the certificate information, all of this is spoofed. So what I've done is I've taken what looks like a pop-up window and I've spoofed it inside the contents of a website. So the user's thinking, oh, this is a browser, something the operating system's showing to me, but in reality, it's just the content of the website itself. Okay, and so anyway, so we call this Chrome, by the way. The original word Chrome is all the stuff, like the browser, like the toolbar and the like scroll bar and the thing at the bottom, like that frame is called the Chrome of the browser itself, okay? So to check this, what you need to do is you need to drag it into the Chrome of the browser or past the Chrome of the browser in order to see whether it's actually real or not. So, so pop-ups are dangerous. As a result, now pop-ups aren't allowed, okay? There's two things you can do. You can open in a new tab. That's why we have tabs. It's also convenient. I mean, there's a lot of nice things about tabs, but the one main reason for tabs is from a security perspective, because the tab is always in the Chrome of the browser, okay? It's not in the website ever. There still are pop-ups. So sometimes actually Concordia, I've seen pop-ups, and it's always annoying because Safari tries to suppress them, but you can ignore it and have it actually pop up. But it will pop up a completely new window, you know, like it won't pop up a small window over top of the old one. Like it will just give you a completely new window, okay? So you can ask for a completely new tab, or you can ask for a completely new window, which will be the same size as the original window. But this idea of a small window over top of an old one just doesn't, it's not a thing anymore. But you do have to be careful. So the variant of this attack that you see a lot actually is you'll go to a website and an error message like this will pop up. And you think that this is from the operating system because it looks like an error message from the operating system, but it's actually just in the content of the website. So the website's showing it to you, usually asking you to do something. And then the other thing they do is they can actually trigger a real error message. So you can ask the operating system, hey, actually do an error message, give it to the user in an error message. But then all the user can do basically is either say okay or not. Like you can't get them to like change their password or install things or things like that. You can show them some information and they can do it. So then they'll put the actual attack is in the content. So they're like, hey, there's some issue, you need to phone this number immediately, or that kind of thing. So that's another like kind of way of doing an attack. So you think that message is coming from the operating system, it's actually the operating system displaying it on behalf of the website. Okay, so what can we do? We looked last class at what you can do, how you can obtain a valid certificate. And there's a whole subtree here. The subtree is all the subverting all the issuing processes. So like breaching a CA and messing around with the automated emails and things like that. Then today what we looked at is instead of trying to get a valid certificate, you could just use an invalid certificate. And so this could be like you just throw an invalid certificate in, it warns the user, and you don't care because users are going to click through the warning anyways. It could be that you're exploiting some error in the software. So like the way things are parsed, like null characters, basic constraints not being checked, the go-to fail error that we saw last class in Apple would let mismatched domains go through. You can do a cryptographic attack. We didn't talk about that one. If you are able to steal a certificate, then you're worried that it's going to get revoked. But then you can do things about the revocation, like changing the response or dropping the response if OCSP is used. And then you can try and to use no certificate at all. So you can either strip all references to SSL inside of HTTP, well, inside of HTML websites that you see. You can do the spoofing attack picture-in-picture. We didn't really have a slide about this, but you can put locks all over your page. Sometimes websites have these things called favicons. So like, for example, you see Concordia here has a logo that's displayed here. That logo actually used to be up in the address bar. And so if you made your logo a lock, then you would get a lock in the address bar. It wouldn't be in exactly the right place. It would be somewhere else, but it's sort of there. And for a user that doesn't know the difference, they might believe that it's a lock, even though it's not an HTTPS lock. It's just a picture of a lock that's somewhere near the address bar. Okay, so the entire attack tree is on Moodle if you want to stare at it for a little bit. Okay, so we took 3 lectures to go through this super big attack tree. So why did we do it? What was the purpose of doing all of that? So the first thing I want to do is I want to show you that these evaluation methodologies, the first 3 that we've seen, even though they're high level, like STRIDE, evaluation frameworks, and attack trees, you can drive them to a very deep level. So the paper that I showed you on evaluation frameworks that compared the password alternatives, that's a very detailed paper. It was published at the very top security conference. It's like 40 pages long, and it's just an evaluation framework. That's all the paper is, okay? And this is an attack tree that you can, that takes 3 lectures to go through or whatever, okay? So these methodologies, even though they're very high level, you can be very detailed and you can be very thorough with them. The second thing is that to do an attack tree, if you don't know anything about HTTPS and how it works, are you going to come up with half of the attacks in this tree? No, obviously not, okay? Even if you know how it works, you might not come up with them until you see someone else do them in real life, kind of thing, okay? So that's what makes attack trees hard, is that you need domain knowledge as well. So you can't just go straight to security evaluation methodology without knowing anything about the system, okay? So it's unrealistic to think that on the first day of a job, someone hands you something, you don't even know how it works, and you're going to figure out whether it's secure or not, okay? You have to spend a lot of time figuring out how it works before you think about security. The nice thing I like about the attack tree is that it's very convenient if you want to merge together technical attacks and non-technical attacks, okay? So some of these attacks are just like, hey, the user's going to see an error and they're going to click through it. Or, hey, maybe you're a government. Maybe you could go over to a CA and tell them that by law they have to give you the private key, okay? Those aren't technical attacks, okay? But they're in the tree alongside, finding security flaws in the AES algorithm, in terms of how it does its initialization vectors, which is highly technical and cryptographic in nature, okay? So attack trees don't care whether the attack is technical. They don't care if it's non-technical. And do you know who else doesn't care? The adversary, okay? The adversary doesn't care, right? If they can attack a system using a non-technical attack, that's great, okay? They don't have to do the sophisticated, finding programming flaws or cryptographic flaws or things like that. If there's some human being that they could convince that they're someone that they're not, and they can bring down the whole system that way, that might be the best approach, okay? So when you defend against things, you want to think about all the non-technical attacks as well as the technical attacks. The structure helps you see new attacks. So like, for example, here we had like, you obtain a valid certificate, you use an invalid certificate, you use a revoked certificate, you use no certificate, and then you might say, well, what else is there? Like, you could use a expired certificate. It lays down a pattern. So once you get a couple of them, you can say, oh, there might be other cases, and you can see what it is, okay? So that's another advantage of the attack tree, is that you can see related attacks. And then if you trace from the root all the way to a node, it tells a story of the attack, right? So won't do this a million times, but I'll do it once so you can sort of see what I mean. So my goal is to see, okay, so there's some user and they're using HTTPS. I'm in the middle, I'm seeing all their traffic, but because it's over HTTPS, I have no idea what they're talking about, okay? So what am I going to do about it? Well, I'm going to try and get the tunnel pointed at me, okay? To get the tunnel pointed at me, I need a certificate for the website that they're going to. So I see them going to Google, I want to read that traffic. I need some sort of Google certificate, okay? So I'm going to try and obtain a valid certificate. And the way I'm going to do it is I'm going to trick the CA into giving me a certificate for Google, even though I'm not Google, okay? How am I going to do that? Well, you know, the CA, they have this fully automated system, and they'll send an email, and the email will go to anybody that owns the address sslcertificates@gmail.com. Okay? I'll register that email address, I'll get the email, I'll click on it, then I'll get the certificate, and now that I have the certificate, I'll get the tunnel ended at me instead of Google, and then I'll read the traffic. Done. Okay? So there's a complete story of what the attack is when you go from the root, the root of the tree all the way to the leaf. And you can do that for every path through the tree, and it should tell you a story of the attack. Okay, so it's a lot nicer than just a list of attacks. You could do this, you could do this, you could do this. Okay, so that's it. You've seen an attack tree. Is there any questions about the attack tree or about HTTPS or anything that we talked about? Yeah.
I had a question. So in the certificate, we see the expiration date.
Yeah.
So when you were talking about revocation, like why can't we just see the date and
Oh, sure. So expiration, I didn't put a slide in on. I could have put one on. It's actually one of the most common errors you see because it happens for all sorts of legitimate reasons. People just forget. So when I get a certificate, it's only valid for 2 years. And the idea is that if someone steals my key and I know about it, then I can revoke it. But it's also possible that someone steals my key and I never learn that they do, right? And so the idea of expiration is just so that attacks don't go on forever. It's not going to work for another 10 years or 20 years. Eventually, it's going to stop working. So that's why the expiration is there. Generally, so it's an independent thing than revocation. So you have revocation, which is like, I want to cancel this today, even though it hasn't expired. And there's like, this certificate's no longer valid because it's expired.
So if a certificate is revoked, then the date doesn't change.
Yeah, if the certificate's revoked, then the browser will be happy with the fact that it's still not expired, but it's going to be unhappy with the fact that it's revoked, and so it's going to reject it for the second reason, not the first reason. Yeah. Yeah.
What kind of questions do you expect about attack trees in the exam?
Okay. What kind of questions can you expect on the final exam about attack trees? No one cares about the answer to that, right? Okay. Probably not going to ask you to draw an attack tree. It kind of is hard to mark. I've done it before, but it's like everyone does something different and it takes forever to mark. I might ask you concepts about it, maybe in the context of a multiple choice, or even a true false would be easy, like is it true, like blah, blah, blah about attack trees, so that kind of thing. I'll ask you questions about HTTPS, so the stuff that was inside the tree. And yeah, in that case, it might be, I tend to ask more conceptual questions. So I might say, here's a scenario, imagine this happens, then I'll ask you something about it. And the answer will have to do with it.
Is there any other methodology other than just 3?
Okay, so these 3 are the high-level methodologies. So they're the things that kind of work on anything. So they'll work on hardware, software, whatever. Yeah. Then from here on, we'll go to methodologies that are specific for something specifically. Yeah. So one thing I don't cover because other courses cover it, but you probably have heard of, is like say I give you code and I say, is this code secure? right? You can do attack trees and you can think about stride or whatever, or you could use something that's designed exactly for code like static analysis or dynamic analysis or that type of thing, right? Now, the problem with static analysis is that's great if you have code, but what if you have a policy or procedure, or you have an organization, or you have hardware or whatever, then you can't do static analysis, yeah? So anyway, so you have a set, and same with like for cryptography, for example, what's the methodology? Well, you do a security proof. So you do some mathematical proof that it has certain properties based on assumptions. The problem with these methodologies in the context of this course is, I would have to spend half the course on coding before you could really understand static analysis. Or to understand a security proof, you would have to learn all about crypto before you can understand a security proof. So that's why we put the emphasis on these high-level methodologies at the first. But the answer to your question is no, they're not the only three. Like there's a million different methodologies, but these are the three biggest, I would say, for general methodologies that work on anything. And then the rest of the methodologies will be specific methodologies for specific kinds of things. Yeah. So we'll look at a couple specific things, like we'll look at usability. So we'll look at a methodology called cognitive walkthroughs. That will be your assignment 2. The next topic we'll cover is social engineering. This I cover not because it's a methodology, but actually because there's an absence of methodologies. So I'm going to show it to you because there actually is no real good methodology for it. And if you try and write down your ideas about a methodology, you'll see that they don't really work because you're talking about humans and psychology and things like that. Yeah. So anyways, and then another question that's some people have asked, and I always think I should answer it, but I always forget to say it, is for your projects, you do not have to do an evaluation framework or an attack tree or stride, okay? You can do any security as long as you're talking about why you think something is secure and how people are concluding it's secure and what security means. That's already methodology, okay? It's already an evaluation of security. So I think a lot of students think that you have to do an evaluation framework or you have to do an attack tree. And so a lot of times there's projects that have them even though they don't need to be there or they don't even make sense. Like it's just like the student felt like they had to do it, so they did it anyways, even though it didn't really make sense, okay? So in your projects, do not do an attack tree or an evaluation framework unless if that's actually what you want to do. You don't have to try and squeeze that in to make it fit under the theme of the course. Yeah. Yeah, so the sample questions, I think there's some on the website. Yeah, so there's some at the very end. They're old, and so a bunch of them aren't relevant to the course anymore. Like they're really old. Like so anyways, closer to the exam, ask me again and I'll give you a better sense of like what's on the exam and how useful they are, but there is at least something for you to look at there. Other questions? All right, enjoy your Friday night.